Hey YouTube, welcome back to my data structures in Typescript series. In this video, we're going to go over Fibonacci heaps. So this is the story so far with our heap journey. We started with binary heaps, which had logarithmic insertions, deletions, and updating the key, and then constant time peeking and checking to see if a node was contained in the heap. And the main problem we had with binary heaps was that if you wanted to do any merging, it was O of n plus m. So it's basically linear in the size of the two heaps, where n is the size of the first heap and m is the size of the second heap. So we wanted to improve that, and we did that with the binomial heap. The idea with the binomial heap is to create an isometry between binary arithmetic, binary addition, and this data structure itself, so that the structure of the binomial heap is a forest that is approximately logarithmic in length. So because each binomial tree has 2 to the k nodes, and the fact that the binomial heap has at most one binomial tree for a specific degree k, at most, the length of the root list or forest is logarithmic. So when we're merging, also known as taking the union of two binomial heaps, we're really just performing binary addition, and that gives us a logarithmic runtime, which is log n plus log m, where n is the length of the first heap and m is the length of the second heap. We then leverage the union operation in enqueue and dequeue in insertion and removal, and that's how we're able to maintain logarithmic insertions and removals, and then all other operations stay the same. And then we went even further from the binomial heap and decided to be lazy, and the intuition of the lazy binomial heap is to be lazy. We only need to massage our binomial heap into that forest that is logarithmic in length when we extract the min. So when we enqueue and merge, we're going to just lazily group two groups of forests, just concatenate them. And as a result, these will be now constant time. So we're going to go from logarithmic to constant and logarithmic to constant, which is crazy. But as a result, because we're being lazy with these two operations, we need to do a cleanup step somewhere. So after the dequeue operation, which is also known as extract min, we are going to do a cleanup. And if we look at this with an amortized analysis, we're still able to maintain the dequeue/extract min operation with logarithmic time. So we get these two operations enqueue and merge go down a constant time while still maintaining the dequeue operation. And now this is where we are going with this video. We can go one step further and be even more lazy than the lazy binomial heap, and we get the Fibonacci heap. The Fibonacci heap makes the update key, increase/decrease key, lazy, and we're going to go from a logarithmic runtime to a constant time, and we're still going to have the dequeue operation stay logarithmic. So the main idea of the Fibonacci heap is to make the decrease key operation faster than logarithmic, which is constant. The reason why we want a faster runtime for decrease key is because important graph algorithms like Dijkstra's shortest path and Prim's minimum spanning tree algorithm are heavily leveraging the decrease key operation with priority queues. So ideally, we want this runtime right here to go from logarithmic to constant, and we can achieve that with the Fibonacci heap. So let's look at the existing implementation for decrease key. Let's say we wanted to decrease this node right here, 11. And we decrease it to 10. We don't have to do any swimming up because our heap invariant is not violated. 10 is still greater than 9, and this is a minimum binomial heap. So we're just going to decrease 11 to 10, and then now our binomial heap is still in a valid state. Every node is less than or equal to its children. Next, let's decrease key again, and let's perform it on this node. We want to decrease 12. And we decrease it to 7. So now we're violating our heap invariant because not every node is less than its children. 10 is not greater than 7. 7 should be above 10. So we're going to swim up. We're going to swap 7 and 10. So 7 is going to take 10's place and 10 is going to take 7's place. And we're still not satisfying the heap invariant. 7 is still less than 9. So we want to do another swap or another swim or another bubble. And we do that. We're going to swim 7 up, and now we swim and swap 7 and 9. Now our heap invariant is satisfied because 7 is greater than 5. 5 should be on top of 7 because 5 is smaller than 7. And our heap invariant is now satisfied again. So this is the existing implementation for decrease key. And the runtime for this is log n. The reason why it's log n is because our tree has 2 to the k nodes, and in the worst case, 2 to the k is n, right? Because we have just one tree. So that means that the number of levels a node has to swim up in the worst case is log n. So the decreased key operation is log n for binomial heaps and still lazy binomial heaps. So let's use some intuition and inspiration from our lazy binomial heap and be lazy with the decreased key operation as well. Do we really need to swim our nodes up the entire tree? What if we just simply cut the whole subtree and add it to our main root list? So going back to the example of our binomial heap, let's say we wanted to decrease this node right here, which is 10. We decrease it to 3. And at this point, we are violating our heap invariant because 3 is less than 9, so 3 should technically be 9's parent. But now we're going to try doing the lazy implementation, and we're not going to swim 3 up because we don't want to take logarithmic time. Instead, we want to be lazy, and let's just add 3 to the main root list. So because 3 is violating the heap invariant because 3 is less than 9, we're going to just cut this pointer right here, cut this parent-child relationship, and put 3 to the main root list with our rest of the forest. So that's what we do. We move 3 from 9's child all the way to the root list. We're not going to propagate it up. So this right here, as you can tell, is just a constant time operation because we're just cutting the subtree off. We're just going to be deleting a pointer. And we're okay with the fact that the tree rooted at 5 isn't a valid binomial tree anymore. This is no longer a valid binomial tree because of the children. We have a child of degree 0 and degree 1, but this is not technically a child of degree 2 because this tree itself only has 2 trees of degree 0. There should be another tree of degree 1 here. So we're okay with this, and I'll go into this later. Let's continue on with our lazy version of decrease key, and let's say we wanted to decrease this yellow node right here from 7 to 2. So we decrease 7 to 2, and now we're violating our heap invariant again. And instead of swimming 2 up, we're going to cut this pointer right here, and then move 2 to the main root list with the rest of our forest. So we cut that pointer, and then we move 2 up to the main root list with the rest of our forest. And this is the current state of our heap. Let's say we wanted to decrease 3 to 0. So we decrease to 0, and now we are violating our heap invariant because 0 is less than 1, so 0 should be on top of 1. Again, instead of swimming it up, we're going to just cut this subtree off by just deleting the pointer. So we delete the pointer, and we move 0 up to the main root list with the rest of our forest. And we are left with this current state of our heap. What this means is that there's 3 ways to create messes in our heap. If you remember the dirty dish analogy with amortized analysis, there's 3 ways to place dirty dishes into the dishwasher. First 2 are from the previous video, and these are from the lazy binomial heap. Taking the union of 2 heaps and also inserting into one heap creates messes because we're not doing any consolidation. We're just simply adding nodes to the heap. And the third operation that we've now turned lazy in this video is the decrease key operation. Instead of swimming up keys that violate the heap invariant, we are going to just cut the subtree off and attach it to the main root list with the rest of our forest. Remember that we cleaned up these messes with a consolidation step, and this happened after the extract min operation. Remember that the extract min operation has 2 steps. The first step is to extract the minimum root from the main root list of the forest, and the second step is to consolidate the structure of our heap. It's to clean up the mess that was created from previous operation. And the consolidate step in the extract min operation has 2 sub-steps itself. The first step, 2a, is to sort the root list with bucket sort according to increase in degree. And the second substep, 2b, is to consolidate the root list by continually linking trees until we have at most 1 binomial tree for degree k. So here's a picture of the second step, consolidate. The first step is to sort the root list with bucket sort according to increase in degrees. So remember that we knew the upper bound of the degrees of our binomial trees because it's logarithmic. So we create the buckets, and then we place the binomial trees into their corresponding buckets. And then we perform the bucket sort, which runs in O of t plus log n time, where t is the number of trees and n is the number of total nodes. And the way we classify these trees is according to their degree or order in this diagram. We said a binomial tree was degree k if it had 2 to the k nodes. So we are sorting our binomial trees according to the degree, whereas the definition of degree is a binomial tree of degree k has 2 to the k nodes. But now we have a problem with our current implementation of the heap. We have the problem of classifying our trees. We no longer have binomial trees anymore because we're lazily cutting subtrees. We don't have the guarantee that each binomial tree has 2 to the k nodes. But we still want to classify our trees according to some sort of degree, and we want to do this so we can perform the bucket sort. So this is the current state of our heap data structure that we left off with, and note that some trees will no longer be valid binomial trees. So this one in particular right here is not a valid binomial tree of degree 2. So this is the current state of our data structure that we left off with in the previous example. And note that some of these trees are no longer binomial trees. So this is no longer a binomial tree because we've done some cutting. Same thing for this one right here. So then how do we classify our trees? Before we said a binomial tree has a degree k if it has 2 to the k nodes, but now we can no longer do that because potentially a tree will have less than 2 to the k nodes. So the solution here is to say a tree has degree k if it has k children. So here we're going to say this tree has degree 0 because it has no children, and this definition did not change from the binomial tree. Here we have a tree that's no longer a valid binomial tree, but with respect to our current use cases, we're going to call this tree a tree of degree 2 because it has 2 children. This is a tree of degree 1, and similarly, this is a tree of degree 1 because both of these roots have one child. It doesn't matter that this tree also has another child subrooted with its primary child. Here's a tree of degree 1, and here's a tree of degree 0. So we're moving from this idea 1, that a tree has degree k if it has 2 to the k nodes, to this new definition, where a tree has degree k if its root has k children. So now we are able to classify our new trees according to the new definition of degrees, which is just the number of children. So going back to extract min now works again. 2a, the step right here, is no longer broken because we have changed the definition of a tree of degree k. We are now able to properly clean up, consolidate, and coalesce our heap data structure with the new definition of a degree k tree. And we now say a tree has degree k if it has k children. So this is great. We were able to get the decrease key down to O of 1 runtime, and we were able to fix extract min. But now let's look at the runtime for extract min. Does it still run in log n time? Imagine if we ran a bunch of decrease key operations in a row, which resulted in many subtrees being cut off. So let's look at this example down below. And let's say we decrease this key, and as a result, we had to cut off that child from the rest of the tree. So we cut it off, and it goes to the main root list. So somewhere along here that's not in this diagram. Let's perform decrease key again. Let's say we wanted to decrease that key. And as a result, we're going to have to cut that child off too. So we cut it, and it goes to the main root list. Now let's say we also have to decrease this key, and as a result, the key is smaller than its parent, so we have to cut it off, and it goes to the main root list. And we rinse and repeat. And finally, we're left off with this binomial tree right here. Because our tree sizes are not well constrained, the size of our forest can now end up being linear instead of logarithmic, and this means extract min runs in O of n time. So below are two diagrams of root lists or forests that result when we just run a bunch of decrease key operations all willy-nilly. We just cut off a bunch of children, and we're left off with this data structure that now has a linear length, and we no longer have the logarithmic length. That happened before because the sizes of our binomial tree grew exponentially by powers of 2. So here in the diagram below, we have a tree of degree 0, degree 1, degree 2, and degree 3, and the number of nodes increase exponentially. We have 2 to the 0, which is 1, 2 to the 1, which is 2, 2 to the 2, which is 4, and 2 to the 3, which is 8. And then because our binomial heap was a root list of binomial trees, and at most we can only have one binomial tree for degree k, this is just counting in binary, and that means at most we have log n roots of our main root list in the forest. So we want to mimic something like this. We don't want our forest or main root list to grow into a linear length. So the solution is to allow our trees to become only somewhat imbalanced, and we'll slowly propagate this information to the roots of trees. This will be clear in the next few slides. So the new rule, in order to maintain our logarithmic forest length, is this following rule. Parents can lose at most one child, and if a parent loses two children, then we also cut the parent off from the grandparent. So we basically propagate the cut up if it loses more than two children. So we basically propagate the cut, and we cut the parent itself from its parent if it loses its second child. So think of this rule as the idea that grandparents want lots of children, and if the parent loses two children, the grandparent's going to be like, I don't like you anymore, I'm going to kick you out myself. But notice this rule has a recursive definition. It can propagate up. After the grandparent abandons its first child, if it abandons its second child, then its parent itself will cut off the grandparent. So you can see how this information is propagating up to the root of our trees. So let's look at this example. This is an example of a binomial heap. We have a binomial tree of degree 4. Let's say we wanted to lazily decrease the node highlighted in yellow, and as a result, we have to cut off the node from its parent because the node is now less than its parent. So we want to move the node to the root list. So we cut off the link from the parent and child, and we're going to mark the parent, and here it's just highlighted red. In the code, we usually mark it with a Boolean flag, and here we're just going to mark it with a red highlight, and we mark it, and then we move the child to the main root list. What the mark represents is that the parent has lost one child. So in the future, when we delete another child, we can check to see if the parent has already been marked. That means the child being removed is currently the second child being removed. So then we can propagate the cut up. Let's say we wanted to lazily decrease the key highlighted in yellow, and as a result, the node's value is less than its parent. So we have to cut the child from the parent and move it to the main root list. So we cut it, and then mark the parent, and then move the child to the main root list. Now let's say we wanted to lazily decrease the key highlighted in yellow again. As a result, the node's value is now less than its parent, so we have to cut it off and move it to the main root list. So we cut it off, but now we notice that the parent has already been marked. So this yellow node that's being removed is the second child that the parent has lost. And now we have to cut off the parent itself from its parent because at most, a parent can only lose one child. When it loses two children, it's gone, and we have to propagate the cut up. So we're going to cut off this parent as well, now highlighted in yellow. And we're going to move both of the yellow nodes to the main root list. So we do that. And this is our current state of our heap. Notice that the implementation of decrease key has changed a bit. We now have the limitation that parents can only lose up to one child. When it loses two children, we're going to cut that parent off itself. And this is to ensure that the number of nodes in a tree still grow exponentially. So now what this whole limitation gives us is it gives us back the guarantee that the length of our root list is approximately logarithmic. And now extract min runs in log n again. So the entire purpose of having this limitation that a parent can lose at most one child is so the sizes of our trees grow exponentially. And because of that, our root list or forest will have a logarithmic length, and we need that guarantee for extract min to run efficiently in log n time. So now, because we have this rule and idea that a node can only lose up to two children, we now also have the idea of a maximally damaged tree. A maximally damaged tree is a binomial tree of degree k, which has been maximally damaged by cutting off subtrees from the lazy decrease key operation. So this is a tree of degree 0, and it has no children to cut off. We now have a binomial tree of degree 1. However, we can't cut off any children because if we do cut off its single child, it's no longer a tree of degree 1, so we leave it. We now have a binomial tree of degree 2, and notice how we still can't cut off any of its children because if we do, then this will no longer be a tree of degree 2 because we need at least 2 children. But we are allowed to cut off this node, leaving the root with only 2 children. So we're going to cut this node off from its parent and then mark it with red. And notice how these numbers represent the number of children each node has. We cannot cut off any more children because if we do, this will no longer be a tree of degree 2. And this is the current state. So now we have a binomial tree of degree 3. And as before, we can't cut off any children because if we do, then this is no longer a tree of degree 3. Remember that our new definition of a tree of degree k has k children. But we're allowed to cut off these subtrees right here. So we're going to go and do that. So the first thing we can do is cut off this child right here. So let's do that. And we cut it off. So notice that this node right here no longer has a child. So notice in this tree, we want to delete the branch that has the most nodes because we want to maximally damage this tree. So let's cut off this branch first right here. So we cut that subtree off, and now we cannot cut this child because if we do, then this node right here will lose 2 children, and we would have to cut off this parent. But then if we cut off this node from 3, that means 3 will only have 2 children right here, and this will mean that this tree is no longer a tree of degree 3. So we are done. This is maximally damaged. So here's just for more clarity, we cannot cut this node off without triggering a cascading cut. Here is a binomial tree of degree 4. And again, we cannot cut off the second layer of nodes because that would mean the tree has less than 4 children, but anything underneath the second layer is fair game. So we can start chopping / cutting away at these nodes. So this node right here has no children, so that's fine. This node right here has 1 child, so we can cut off this one right here. So let's cut it off. And we cut it off. We're moving on to the next subtree, and we're going to cut off the branch with the most nodes first because we want to maximally damage this tree. So let's cut off this right here. So we cut that off, and then we can no longer do any more cutting because if we do, we're going to trigger a cascading cut because this node will lose 2 children, and then this node itself will have to be cut off from its parent, meaning that the root node will have only 3 children, and we need to have 4 children. Here, let's move on to the next subtree. And we want to delete an entire branch of one of its children. And we want to choose this one because this has the most children. We want to maximally damage this tree. So we're going to remove this entire subtree right here, rooted at 2. So we do that, and now we move on. We see that we can cut this node right here without triggering a cascading cut. So we're going to delete this one as well. And we delete that as well. And notice how we cannot delete any more nodes without triggering a cascading cut to the main child of the root. One thing to notice right here is that a maximally damaged tree of degree k is a node whose children are maximally damaged trees themselves of order 0, 0, 1, 2, 3, all the way to k minus 2. And this is the beautiful pattern that comes up that gives this whole data structure its name. I've been avoiding saying the name in this video because I wanted to kind of lead you guys to this name Socratically with the Socratic method, and this is the Fibonacci heap. The reason why it's called a Fibonacci heap is because the number of nodes in maximally damaged trees form the Fibonacci sequence. So here we have 1, 2, 3, 5, 8. And this is a theorem that the number of nodes in a maximally damaged tree of degree k is the k plus 2 Fibonacci number. And the proof of this is omitted for this video. And here is the final verdict. We are moving from the lazy binomial heap to an even lazier implementation of it, and we're going to call this the Fibonacci heap. The Fibonacci heap is the lazy binomial heap with the addition of the lazy decrease key. So here, everything is the same as the lazy binomial heap, except the decrease key, which is going to be now O of 1. And this is the most efficient we can get with decrease key. This is heavily leveraged in graph algorithms like Dijkstra's shortest paths and Prim's minimum spanning tree. So in summary, we start off with the lazy binomial heap, and we want to be even more lazy. We want to make decrease key faster because it's important for some graph algorithms. So we want to improve decrease key from log n runtime to constant. And the way we do this is to stop swimming up nodes when they violate the heap invariant. Instead, we're just going to lazily cut off the subtree instead of swimming it up. But now we need to change the definition of a degree k tree. Before we said a tree has degree k if it has 2 to the k children. But now, since we're cutting subtrees off, we no longer have that guarantee. So we're going to change our definition of a degree k tree and say that a tree has degree k if it has k children. This fixes the consolidation step of extract min because we need to sort the trees according to the degree with bucket sort. The next thing that we notice is that if we just performed a bunch of decrease key operations, then the length of our forest would grow into a linear length. So we still wanted our root list / forest length to be logarithmic. And for it to be logarithmic, we need our tree sizes to grow exponential in length. So the idea was to allow our trees to become slightly imbalanced, but still allow it to grow exponentially. And we do this with the rule that a parent can never lose more than 2 children. If it does, it gets disowned from its parent itself. So when cutting a node, we mark its parent. And when it is already marked, that means we are cutting the second node off. So we're cutting the second child off. So we also cut the parent off. The next point is that Fibonacci heaps are theoretically optimal. So extract min is still log n and all other operations are now constant. But in practice, Fibonacci heaps are usually outperformed by simpler heaps due to the overhead. You'll see in the next video with the implementation that there's a lot of pointers pointing to things, and it's quite complex to create, so oftentimes it's better to use a simpler heap due to the complexity and overhead with storage. But the Fibonacci heap was created as a theoretic optimal data structure for the algorithms that heavily use extract min / decrease key. So for algorithms like Dijkstra's shortest path and Prim's minimum spanning tree, we use a lot of extract min operations, and that's why the Fibonacci heap was created, because we wanted constant time operations. So that was the Fibonacci heap. This is the final verdict. We now have constant time decrease key while still maintaining the logarithmic extract min. I hope you guys enjoyed the video, and I'll see you in the next one where we'll go over the implementation for the Fibonacci heap. See you then.